Alright, so today we're going to be looking at problem 2.39 in the textbook. To begin with, they give us an image of a spherical conductor with two cavities. The cavities have radius A and B, and they each have a charge placed in them, QA and QB respectively. And the conductor as a whole is a sphere as well, with radius R. So the first question they ask us is to find the surface charge densities, sigma A, B, and R. And the simplest definition of surface charge density is going to be the charge enclosed as over the surface area of the shape. So if we just simply plug in for sigma A, B, and R, the charge enclosed, which for A is just going to be QA, over the area, which is going to be 4 pi r squared, but in this case R is going to be A. Same thing for B, and then for for sigma R, we're going to have to include both of the charges for these as well. Next, they ask us what is going to be the field outside the conductor. So if we start with Gauss's law, we can start with this equation right here. So next, the first step is going to be to pull the electric field out of the integral. We can do this because we know spheres are particularly symmetrical, and we're talking about electrostatics, not electrodynamics. So the field outside of the conductor is going to be constant, which allows us to pull it out of the integral. So this is going to leave us with just the field times the integral of dA, and the field times the integral of dA equals the charge enclosed over epsilon naught. So moving on down here, we can see that the integral of dA is just going to be the area. So, and then if we plug in the charges enclosed, we'll have QA and QB, and we'll have to add them together. So we will move on to have the electric field times the area, which is going to be 4 pi r squared, equals QA plus QB over epsilon naught. And then if we divide both sides by the area, we will end up with the electric field equal to QA plus QB over 4 pi epsilon naught r squared. Next, we are asked what is the field within each cavity. So again, this is going to be the same logic as previously, except instead of looking at the conductor as a whole, we're going to draw our Gaussian surface just around the cavities. And same as before, the field is going to be constant because of symmetry and electrostatics, not dynamics. And this time, the Q enclosed is only going to be one of the charges at a time. So the field within cavity A is going to be QA over 4 pi epsilon naught A squared this time to account for the radius. And then similarly, the field for the B cavity is going to be QB over 4 pi epsilon naught B squared. D asks us what is the force on QA and QB. And this is actually going to be 0 because we know that if a charge is introduced to a conductor, the particles inside the conductor are going to move around until the net field is 0. So if we look at one of these charges at a time, the field produced by, say, A, the conductor will shift all of its particles around it. So if QA is positive, all of its negative particles are going to come surround it, and B will eventually feel a net 0 pull until the particles have shifted. Same logic goes for B. So any external, quote, external field, external referring to either whichever charge you are not looking at, it will be negated by the internal field created, the induced field created by the conductor. So this should say induced. Lastly, we are asked which of these answers would change if a third charge, QC, were brought near the conductor. And we can immediately look at A and C, and these two questions are asking us to find a particular value relating to each charge. So A and C would probably just have an additional answer, so maybe sigma C, and the field within the C cavity or outside outside the conductor. But using the same logic we just talked about in D, in the sense that the conductor will adjust its particles as needed to create a net zero field, a third charge would have really no effect on the forces on QA and QB. So this means that our last option is that B, the field outside the conductor, would change. And yeah, feel free to let me know if I messed up anywhere. Thank you.